Welcome to my YouTube channel Modi Mechanical Engineering Tutorials. In this video I would like to explaining about TTT diagram and cooling curves. So how cooling curves it will be affect to make a transformation from austenite to the different phase. By the mode of the non-equilibrium cooling, so that austenite it will be transforming into the pearlitic structure, bainitic structure and martensite structure. So this theory we already discussed in my previous videos. So basically this non-equilibrium coolings onto that particularly high temperature stable austenite, or you can say above the 723 degrees centigrade. So then after it will be transformed into the different kind of structure just below of this temperature line. So that will be also known as a lower critical temperature line as per the iron carbon diagram. So today in this video I would like to take a TTT diagram for hypoeutectoid steel. So how the cooling curves will be effect onto the hypoeutectoid steel. So as we already discussing into the basic TTT diagram in my last theory, so x-axis that will be the representation of time of log scale, and onto the y-axis it will be the temperature in degree centigrade. So here 100, 200, 300 and up to the 800. So as per the general TTT diagram, these lines it will be act as a transformation start, and these lines it will be act as a transformation ends. This horizontal line that will be the representation of starting of martensite, and up to this it will be the finish of martensite. So that will be MS. So that will be indication as the starting of martensite and finish of martensite. So this is a total area, or you can say martensite structure is being found over here, and around 550 degree centigrade. So this temperature range it will be separate out of the different phase of the pearlite and bainite. So just you can see from 550 degree centigrade to up to the 723. So that will be the area of pearlitic structure, or you can say pearlite, and just above this temperature line to the starting of the martensites, so that will be a bainitic structure. And these curves it will be known as a nose of the curve, and from this side so that will be the unstable austenite. So if you want to make a more precise phase, so that nearer part to the 723, so that will be the generation of coarse pearlite, and at around 550 degrees centigrade or just above this temperature line, so it will be the formation of fine pearlite. Similarly for the bainitic regions, so just below of 550 degrees centigrade, so it will be the formation of upper bainite, and just above the starting of the martensite lines, so that will be known as a lower bainite. So basically bainite is nothing but that will be the proper mixture of ferrite plus cementite, but that will be into the structure it will be defined as a trochite structure. And similarly for pearlite, which is also made with the ferrite plus cementite, but that will be making a laminar layers. So if transformation line from austenite to the different phase, so that will be the phase of making a pearlite region. So in between of the two transformation lines it will be the gamma austenite plus pearlitic structure, and from these regions that will be gamma plus upper bainite, so UB. Similarly, from these regions it will be gamma plus lower bainite, so LB, that means lower bainite structure. And just below the starting of the martensite formations, so that will be the gamma plus martensite. So just you can see here it will be the starting of the martensite. So at this point that will be the 10% of martensite is being formed. Up to this it will be the 50% of martensite is being found, and for this that will be the 100% martensite is being found. So that is the total region of the martensite structure. Now the important part of this theory, so which cooling rate is being preferred, or you can say which heat treatment process is being preferred, or you can say by which cooling curve you will get a different structures like a coarse pearlite, fine pearlite, upper bainite, lower bainite, or you can say martensite. So basically these structures it will be depends upon my requirements of the applications. So according to that requirement of my applications, I would like to select such a cooling curve, so which will be transform our stable austenite to the different phase. So now let's see the first cooling curves, and that will be the CCR, or you can say critical cooling rate. So just you can see the critical cooling rate. So as shown into this figure of TTT diagram for the hypoeutectoid steels. So what happens? So the slowest possible cooling rate by which the fully martensite structure can be achieved. So that will be only possible if you can controlling the cooling that will be touched at your nose of the curve. So such kind of cooling rate it will be known as a critical cooling rate, or you can say CCR. So just you can see the graphically it is a tangential to the nose, or you can say knee of the TTT curve. So just you can see this CCR will be touched at the nose of the curve. So hence it just avoids the transformations to converting into the pearlite and bainite, so which is the soft phase of the steels. But by the application of CCR, which will be passing through the nose, so that will be directly converting into the martensite phase. So austenite it will be directly converting into the martensite phase with the minimum cooling rate, so that will be known as a CCR. So just you can see if any cooling curve which will be passing before the critical cooling rates, so obviously that will be directly austenite it will be converting into the martensite structure. So by the CCR only the martensite phase is being formed. Hence the critical cooling rate is defined as the slowest rate of the cooling at which all the stable austenite that will be transforming into a 100% martensite phase. So basically the some of the factors that will be affecting onto the CCR, and first one that will be the compositions. So into the critical cooling rate that will be decreases by the increasing the carbon content, or you can say by the addition of the alloying element other than the cobalt. So what happens, by the addition of the carbon percentage into the compositions of the steels, so that transformation lines it will be shifted towards the right sides. So both the transformation lines it will be shifted towards the right side of that particular curve. If you are reducing the weight percentage of the carbon, so this transformation line it will be moved by the left side. Second factor that will be affect onto the CCR, that will be the quenching temperature. So basically for the higher quenching temperature, so that will be having a faster cooling rate. And third, that will be the purity. So the purer steel, so the lesser the critical cooling rate. So these basic three factors which will be affecting onto the critical cooling rate. So in simple way, the curve which is passing through the nose of the transformation line. So which will be transforming stable austenite to the martensite phase. So now we will discussing with the different cooling rates to transforming stable austenite into the various phase. So starting with the slow cooling rate. So just you can see there will be the 2 points x1, x2. Just you can see the cooling curves. So this cooling curve which is corresponding to the slow cooling curve, or you can say that will be the annealing process. So into the annealing process it will be the furnace coolings, or you can say cooling under the sand. So which will be preferring the slowest cooling rate. So at this cooling rate, this stable austenite which will be transforming into the coarse pearlite. So just you can see that curve, it will be intersecting at a transformation start at x1, transformation end at x2. So in between it will be the 100% austenite. Now that will be converting into 100% coarse pearlitic structure. So by this slow cooling curve, so that will be having a hardness, or you can say measured hardness of that particular component, or you can say phase, that will be RC15, which is smaller as compared to any other components, or you can say which is soft into nature. Now we will discussing with the isothermal transformation process. So just you can see the cooling curves. Just you can see by these cooling curves, or you can say isothermal cooling curves, the specimens takes from critical temperature and placed into the salt bath at a predetermined temperature. Hold it here for the complete transformation, which is started at x1 dash point, or you can say here, and which will be ended at your x2 dash point. So in these transformations it will be the formation of more stable kind of structure as a pearlitic structure. So that will be having a good hardness as compared to our annealing process. Now third cooling curve, which will be preferring a cooling into the air, or you can say normalizing process. So just you can see, so into the air cooling, or you can say into the heat treatment process wise, that will be the normalizing process. So that will be intersecting at this point, or you can say x1 double dash to x2 double dash point. So which will be having a transformation start and transformation end. So by the air cooling or normalizing process of the heat treatment, this stable austenite now which will be converting into the fine pearlitic structure. So this pearlitic structure, it will be having a hardness around RC30 number. So which will be higher than the coarse pearlitic structure. So by the air cooling, it will be get a good structure as compared to the annealing process. Now we will discussing with the cooling curves, which will be followed by a slow oil quenching. So just you can see, but this cooling curves, the microstructure will be consist of the medium and fine pearlite with the hardness of around RC40. So that will be the category of either it will be the fine pearlitic structure, or you can say upper bainitic structure by the following of slow cooling of the oil quenching process. Now we will discussing the cooling curves that will be having a quenching process, but initially it will be the formation of the fine pearlitic structure for the shorter period of time. Then it will be converting into the martensite structure. So just you can see the coolings. So just you can see by this quenching process, first of all, these cooling curves will be intersect at a transformation start. So that will be the region of the fine pearlitic structure. So then austenite, now it will be converting into the fine pearlitic structure. Now the coolings, it will be moving on and it will be into the region of austenite and upper bainitic structure. Once again, these cooling curves, it will be touch the same transformation start point. So once again, it will be converting into the unstable austenite, and then it will be with the help of quenching process. So it will be directly converting into the martensite structure. So by such kind of cooling onto the stable austenite to the fine pearlitic structure, and by this quenching process, it will be directly formation of the martensite. So you will get a RC, or you can say hardness, which will be around RC 64. And last cooling curve, which is faster than the CCR, or you can say critical cooling rate, just like this. So as shown into the diagram, so this cooling curve which is faster than the CCR, so that cooling curves, that will be the resembles the drastic quenching, and it is rapid enough to avoid nose transformations. So that will be never touch the nose of the curve. So what happens? So it remains austenite till to martensite starting line. So that will be intersecting directly to the martensite start point. So that will be the P point. So what happens? The transformation to the martensite structure, so which will be having a higher hardness. So by this rapid cooling curve, what happens? This stable austenite, which will be directly converting into the martensite structure. So without converting into any pearlitic structure or bainitic structure, but stable austenite, which will be directly converting into martensite structure. If you control the cooling curve, that will be before the CCR. So by this cooling curve, you will get a maximum hardness is being present into the steel structure. So basically all the cutting tool materials which will be followed by the rapid cooling process onto the steels. So that austenite phase, it will be converting into the martensite phase. So that will be having a capabilities to cut any form of the steel materials like pearlite or bainite structure. So this rapid cooling process, that will be known as a hardening process. So just summarize this TTT curve. If you following the annealing process, or you can say slowest cooling rate, so this stable austenite which will be converting into coarse pearlitic structure with the RC of 15. If you followed by normalizing process, or you can say air cooling process, so this stable austenite which will be converting into fine pearlitic structure. If you followed the slow oil quenching process, so our stable austenite which will be converting either into the fine pearlitic structure or nearer to the upper bainitic structure, which will be having a RC around 30. If you are controlling the cooling which will be passing through the fine pearlitic structure for the shorter period of time, then it will be converting into the martensite structure, so which will be having a RC around 64. But if you controlling the cooling rate which will be passing through the nose of that particular transformation start curve, so that will be known as a CCR, so which will be help to converting our stable austenite into the martensite structure. But if you are controlling the cooling before the CCR line, so it always forms a 100% martensite structure. So you will say that the 100% stable austenite which will be converting into 100% martensite phase. Now I would like to draw a microstructure for austenite, fine pearlite, coarse pearlite, bainite and martensite structure. So first of all, for the austenite, just you can see, so as per the iron carbon diagrams of the steel category, so as above the 723 degrees centigrade, so it will be the formation of 100% stable austenite. So that gamma phase is being found at this temperature. So that will be known as a stable austenite, which will be soft into the nature and which will be having a 100% solid phase of the steel at your above 723 degree centigrades. Now I would like to draw a microstructure for coarse pearlite. if you followed the annealing process, so that will be the formation of the coarse pearlitic structure. So let's see, by the annealing process, it will be the generation of coarse pearlitic structure. So that will be the only layers you will find for this structure by the annealing process of the heat treatment process. Now if we are performing the air cooling, or you can say normalizing process, so let's see the microstructure over here. So by the normalizing process, so that will be the formation of fine pearlitic structure. Now just you can see, if we are followed by the slow oil quenching, so it will be making a spheroid kind of structure. So that spheroids, it will be onto its microstructures. So it will be look like this. So that will be your spheroid. So if it will be the bainitic structure, so that will be making a trochite kind of structure. So let's see over here. So these trochite kind of structures, it will be only found with the help of Austenite tempering process. So that will be the interrupted cooling kind of methodology is being applicable onto the cooling rates. So that will be the formation of trochite kind of structure. And finally, if you are performing the quenching process, or you can say rapid cooling, so that will be the formation of martensite structure. So let's say into the martensite structure, which is a hardest structure for the steels. So that will be having a maximum hardness is being present into the steel structures. So that will be the martensite. If you learn about the normal steel, so just you can see, so this is our normal steel materials at room temperatures. So if you want to make such kind of material properties like coarse pearlitic structure, fine pearlitic, bainitic or martensite, so first of all, these normal steels, it will be heated and converting into the 100% gamma phase of the steel, and that will be known as a austenite. Then you will followed by such an cooling process. Either it will be annealing, normalizing, slow oil quenching, or water quenching, or you can say quenching process. So that will be this normal steel, it will be converting into the different properties as per my requirements. So these all are about TTT diagrams, and the cooling course, it will be affect for converting this stable austenite into the different phase of the steels. So I hope you understand this theory. If you like this, then subscribe and share. Modi Mechanical Engineering Tutorials. Thank you so much and keep watching.